is equal to 1. And I think that the multiplication is based on that. I don't remember exactly. I'm not saying that's exactly I don't know. Let me back off on that. But there is a way to put a Lie group structure on this. It was proved, this might be Milner, proved that there does not exist a Lie group structure on this. That was proved in like the late 60s or 70s, somewhere in there, I think. So, so let's see here. Vector fields. So we need to talk a little bit more about vector fields just from their base structure. I think I can get rid of the middle board now. Let me do that. So vector, you guys remember what a derivation is? Oh man, this is just, golly. It just goes everywhere except the board. Look at that. You see that? You see what's happening, guys? Yeah. So we can view, just let me try to get to the point here, because I could easily spend a half hour writing all this stuff out and it really wouldn't get us anywhere. In summary, vector fields can be viewed as derivations on the set of smooth functions on the manifold. So what's a derivation on the set of smooth functions? What does that mean? I just need to write some, yeah, go ahead.
Does it map the function to its tangent?
Maps the function to its tangent vector. Maybe this will, maps the, say what you said again? Maps the.
Is it similar to the directional derivative?
Yeah, I think that's
That's the analogous.
I think you're right. I think it's like the directional derivative. That's probably not wrong. So if we have a smooth vector field and a smooth function, all right, and so he likes to let f go from u to r. So here u is a subset of m. Remember, this is a kind of sneaky thing. To say f is a smooth function on the manifold, it could be that it's defined on a subset of manifold, but then you just extend it smoothly past that by making it 0 outside its domain of definition, essentially, with the magic of the bump functions. So, that's the, I don't know, at this point, 100 pages in John Lee's book that I have not really talked about in class, all of that extension and restriction, careful analysis that I'm not doing in class very much that's in the book. But anyway, then x times f, all right, is a mapping from u to r, defined by xf at the point P is equal to xp acting on f. So important distinction here. If we take f times x like we defined earlier, that is a vector field. If we take, on the other hand, x acting on f, that's a smooth function. So you gotta be careful. This isn't like, vector spaces where we can scalar multiply on the left and the right and whatever, que sera, sera. No, it matters. F is multiplying x pointwise, whereas x is acting on f to give us a new smooth function. Proposition 8.14 simply tells us this: a vector field is smooth if and only if xf is smooth for all smooth functions. So we can judge the smoothness of a vector field by whether or not, when it acts on smooth functions, it gives you a smooth function. And you can check that the following, this is the derivation property I was trying to get you guys to tell me about. But I think you know. So here's how it goes. Right? And so basically, the proposition 8.15, what's it say? It simply says that we can identify the derivations of smooth functions on the manifold with the smooth vector fields. There's a one-to-one correspondence between these guys. All right, so wonderful. That brings us to talking about smooth maps. So what about smooth maps? Let's see, vector fields and smooth maps. So if F is a mapping from, say, a smooth manifold M to a smooth manifold N with or without boundary, right? Then, where was I? Oh, so let's think about that. We already had a way of doing things with tangent vectors. You guys remind me, how did it go? Then, how did it go? We had like DFP did what? Mapping from where to where? From TPM to where? Yeah. Yeah, there's an N over here for sure, but what the point? Where's the, what? F of P. Right. So we're talking about this is this. I call this the push forward, right? Or the differential, if you like, of the map. So, okay, let's think about this. You've got M, right? And you've got N. You got this map that goes from here to here, right? And suppose you've got a vector field, right? You've got a vector field. Vector field X, right? On M. How would you construct a vector field on N?
Taking the differential of every vector.
Yeah, right. You'd like to say, oh, okay, so I'm going to define Y at the point F of P. I'm going to make it equal to what? I'm going to make it equal to DFP acting on what? Acting on XP, right? There you go. So if X is a smooth vector field on M, then we can say, F push forward X, which we'll call Y, is a smooth vector field on N, where F push forward X, at the point F of P is going to be defined to be, Y of F of P, right? Specifically, DFP of XP, right? For all P and M. Now, does this work? Is this like a legitimate thing that we're doing? The answer is no. Well, the answer is sometimes. What's the problem? There are two problems. To have a vector field on N, what do you need? You need to assign a vector to each point in N, right? But it could be that this is F of M, right? The range of F of M, F need not be surjective. F could not, if F is not onto, then you're not assigning vectors to all of these missing points, right? So that's a problem. If it's not onto, this doesn't quite work, right? But it's worse. What if F is not injective? If F is not injective, you could have the situation where F of P1 is equal to F of P2. Let's say it's equal to Q. For P1 not equal to P2, right? There is really no reason a priori before the fact that the differential at P1 acting on V should be equal to the differential at P2 acting on V. So if you think about that, if it's not one-to-one, you can end up assigning at a single point, at this single point Q, you might be finding that you've got two different vectors assigned there. That's not good either. That's not a section of the tangent bundle. Section of the tangent bundle, part of that is it's a function. We're assigning a single vector to each point. So we've got these two issues to run up against. Lack of surjectivity, lack of injectivity ruins the straightforward push forward of vector field to vector field. However, if F is a diffeomorphism, these issues go away because it's onto and it's one-to-one, all right? And so for this reason, we make a definition to kind of take care of these issues. I'll do it over here. Our definition that we would like is called F-related. F-related. So here it is. Definition. F from M to N, smooth. And X, a smooth vector field on M, and Y, a smooth vector field on N, are F related if the differential of F at P of X at P is equal to Y of F of P. Well, this looks familiar, right? In other words, the definition of saying two vector fields are F related is really just saying what? It's just saying the naive construction of the push forward field works. It works. Beautiful theorem to state here, which is that, so this is proposition 8.16, and it simply says that X and Y are F related, X and Y F related, if and only if X of F composed with big F is equal to Y acting on F composed with big F for all F in C infinity N. Now it's not quite that. Let me put some quotes on this because the precise language is for all smooth functions defined in an open subset of N. All right. The proof of this assertion is little more than our definition of push forward. So the way this goes is as follows. We have that X of F composed with big F at P. Well, what's that? By definition, that is by definition X sub P acting on F composed with F. I mean, that's how we define vector field at a point. The vector at the point acts on the function. But hey, by definition, that is df. That's the differential of F big F at P acting on the vector xp acting on the function. Like that's the definition of differential. Just that. And on the other hand, if we look at Y acting on F composed with F at P, well, that's YF acting on F, I mean at F of P, which is by definition Y at F of P acting on F. And that's it, because that's, look, like, see this? look at these two, you know, let me get a different color here so you can pull your eyes to it. Sounds painful. So feast your eyes right here on this formula, and then look at these two. This true for all f, so they're equivalent. So x and y are f related if vector fields x and y are f related if we have this intertwining relation between the vector field, its action, and composition of the function. Proposition 8.19 says that if f is a diffeomorphism, then there is a unique vector field which is f related to x. Let me erase the middle board here and I'll show you guys that. I gotta drive me nuts. Well, something's exciting. It's your sister, huh?
Yeah.
All right, so by the way, example 8.17, nice. But I know my time is limited in here, so I won't write that on the board. But I would if I could. But I can't, so I won't. Where's my marker? All right, so if we have f from m to n diffeomorphism, then we can define and x a smooth vector field on M, all right? Then define y at Q equal to, here's the definition, d f of f inverse of Q of x of f inverse of Q. Here's a picture of what's going on. This is M. This is N. We're trying to define a vector field here at Q, right? So you take that. So what do? Think about this. You take Q and you move it back over to here. Where? At P equals to F inverse of Q, right? You can do that because it's a diffeomorphism. It's got an inverse. Then what? Over here, you've got a vector field, right? So you can look at x at P there. And then what do? This is the x at P. So you simply push it back over here like that. And that is your y at Q. Now I wrote it in the notation f inverse of Q and f inverse of Q rather than P, but that's all that's going on. If you've got a diffeomorphism, you can take the point, get a corresponding unique point on M, find the vector there, push it over here. Because it's a diffeomorphism, you know that's a single vector, all right? And because this is a straight formula, which means that y that we're constructing is uniquely so. So proposition 8.19, which is what I'm talking about at the moment, it says that there exists a unique vector field that is f related if it's a diffeomorphism for a given x. And that unique vector field is this y, which I've just constructed. And so he points out finally, as like to show you that it's smooth, this is kind of pretty. y is a section of the tangent bundle of n, like so, and it's actually the composition of the following maps. So to get from n to m, we use, to get from n to m, we use F inverse. To get from m to tm, we use x, because x is a section of the tangent bundle. And then to get from tm to there, well, that's the differential, which, if you remember that chapter, can be defined as a smooth mapping on, for a diffeomorphism, the differential of a smooth map is in fact a smooth map on the tangent bundles considered. And as such, this vector field is the composition of smooth maps, therefore smooth. That's proposition 8.19. Now, so then he's got a little section on vector fields which are tangent to a submanifold. Like, what do you think that would mean if you've got, you know, submanifolds? Let's say submanifold tangent. So basically, if you have x, a vector words, a vector field, all right, is tangent to S, a submanifold of M. If you, what do you need? You need that XP is an element of TPS, right, which is a subset of TPM, right, for all P in for all P in S. So that would be a tangent to a submanifold, is like that. And then the main theorem he gives, proposition 8.22, gives a nice criteria for judging whether or not a given tangent vector field is in fact tangent to a submanifold. And then proposition 8.23 tells us that if we have a tangent vector field to a submanifold, then there exists an extension of that tangent field to the larger manifold, which is a smooth extension and restricts to the tangent field. So we'll probably come back to this in examples later. I don't want to belabor it here. And that finally brings us to what I've been really looking excitedly to talk to you about today. And we're not going to talk long about this today. I'm just going to introduce it, which is the Lie bracket. All right, so let me just take a step back and let's talk about what we've done so far. We've introduced the concept of vector field, which is really just knitting together, gluing together, if you will, vectors at different points as a new concept, right? It's in the same way we can talk about derivative at a point in Calculus 1 to start with, right? We talk about derivative at a point. Then the next day we talk about the derivative function, right? So vector fields are like the derivative function. And of course, in Calculus 1, you can do much more interesting things with the derivative function than you can with the derivative at a point. In the same way, on a manifold, you can do many more interesting things with vector fields than you can do with vectors at a point. Because vector fields start connecting points to points and start giving you a sense of how things flow together from point to point, and that's ultimately what we're going to see. Vector fields, the existence or non-existence of certain kinds of vector fields are tantamount to the structure of the manifold having certain features. So it's very interesting. Lie bracket is one of the fundamental things that we can do with vector fields in terms of creating a new vector field. We already know we can take, we already learned today, we can take sum of two vector fields and get a vector field, or multiply a vector field by a smooth function and get a new vector field, right? That's a way of getting new vector fields from old. This is a more interesting one. If you take two vector fields, you can define the Lie bracket. So for x, y in the smooth vector fields over a manifold, the Lie bracket acting on a function is defined to be x of y acting on f minus y of x acting on f. This is the definition of the Lie bracket. Now, some questions immediately arise, right? Like, first of all, why can't you just do one of these? Like, why isn't it, a lot of time, like, hey, before, when we took the composition, think about this. When we took the composition of linear maps in linear algebra, was it again a linear map? Like, is the composition of linear transformations a linear transformation? Okay, why not here? Why isn't the composition of vector fields a vector field in this sense? What's the problem? So, example, where are we? You're like over time. I'm almost done. I'm really almost done. I promise. Where are we? Can you guys tell me example numbers? Drive me nuts.
We are 6, maybe.
6?
5.
5. Only 5 examples? Come on.
You had example 1A earlier.
Oh, okay. So let's see here. So if we took, say, x equals to partial x, and we take y equals to, let's say, x squared partial y. We'll just deal with these particular vector fields on the plane. Let's just study these, okay? What's the deal with x, y acting on a function? What's that look like? You've got x, right? And then you've got, you've got x squared and then partial f partial y, right? Which is what? Partial x of x squared partial f partial y, which works out to what? Apparently 2x partial f partial y, right? Plus x squared partial squared f partial y squared. Now that might not look like much to you. Let me write it out again. So we have then is xy, I'll strip the f off for a second here, is equal to 2x partial y plus x squared partial y squared. All right? The question is this a vector field? I hope not, because remember the vector fields at any point are a what? They're the span, they're the sum, the linear combination of the coordinate tangent for the coordinate frame at the point. But the coordinate frame at a point in the plane is just partial x and partial y. But we've got this partial squared partial y squared. That's not in the span of our coordinate frame. And let me just tell you the problem with this guy. This guy's a problem. See, because partial squared partial y squared, when you act on f times g, what do you get? You get fg, what you get is you get partial y of partial f partial y g plus f partial g partial y, right? Which gives you, by the way, partial squared f partial y squared g plus twice partial f partial y partial g partial y plus f partial squared g partial y squared, which, by the way, is not equal to partial squared partial y squared f times g plus f times partial squared g partial y squared, which is this is what we would need for the second derivative to be a derivation. We have that. We've got those, right? But we've also got this, and this is the spoiler. So second derivatives are not derivations. So one last calculation and we'll be done for today. You guys tell me what's yx equal to? For this specific example we have right here, what's yx equal to? So we would have to do x squared partial y, and then that would be acting on partial x, right? How did I get, oh, come on, guys, don't let me do that. Dudes. Come on, guys. Don't do me like that. You guys gotta help me. Don't be like my son is taking linear algebra in the morning, and after I got home, he's like, you wrote 1 = 3 on the board. And I was like, and none of you corrected me? Not cool. He's like, yeah, but you think 1 = 3. I'm like, no, don't think that's how that works. But anyway, yeah, I should have had that. And now this calculation is wasted, but that same calculation goes through with the mixed partial. When you go through the mixed partial on the product, again, you'll see like something similar happens to the mixed partial. I don't want to do it because our time is up, but you can prove that the mixed partial derivative is not a derivation. It doesn't satisfy the Leibniz rule. It doesn't satisfy the product rule. So it's not a derivation, therefore it's not a vector field. Because remember, there's a one-to-one correspondence between derivations on smooth functions and vector fields. Okay? And great. So you notice what happens though. When you calculate yx, you get this. When you calculate xy, you get that. What happens when you calculate xy minus yx? What do you get? Not 0. Actually, no. So in that case, this, well, I should really write. So this and that cancel. You're just left with that. In other words, the commutator of the vector field x and the vector field y is equal to 2x partial y. These are the same commutators that are of interest in quantum mechanics and, you know, ultimately have a lot to do with how we describe nature. Commutator of vector fields. Okay, fine, we take commutators of other things there, but, you know, the idea of a commutator. So in short, we can take the commutator of two vector fields and we get another vector field. And we're going to see that this commutator bracket gives the the set of vector fields on a manifold the structure of a Lie algebra, which we'll define next time and make precise. And we'll actually do the legwork we need to make precise the theorem I wrote over there. But this is my absolute favorite part of what we're doing for a while, because it's this like beautiful combination of both the calculus and the algebra. So I shut up. Thanks, guys.